So welcome to session 2. The first speaker will be joining us online. It will be Dr. Zeng from the Florida State University.
Hello.
Hi, thanks for joining us. You can
Hi.
start with your presentation. Thank you.
Is my audio okay?
It's perfect. Thank you.
Right. Yeah. Okay, so I have like 15 minutes-ish.
Yes.
Okay, well, hello everyone. Good morning. It's evening here in Florida. My name is Zeng. I'm now assistant professor at Florida State University and faculty affiliate with Lawrence Berkeley National Laboratory. I'm very happy to join in through Zoom, although I really want to be there in Japan. I want to share our work on autonomous laboratory for inorganic materials synthesis and discovery. A big motivation for us to build up a lab autonomously is to speed up the synthesis step in materials discovery. We have been working on the battery technology specifically, and one of the emerging concept, for example, is this so-called multi-component or high entropy materials that may offer promising properties for energy storage and maybe some other applications. But when we look at this design space, it's just so enormous, and it's impossible to develop or optimize this kind of material by following a traditional way to do material science. Well, of course, there are many different kind of acceleration tools that we can borrow or we can use to accelerate some individual step. For example, we can use computational modeling to help with design promising targets. We can use advanced characterization technologies to dig into the details of the fundamental of materials property. Or if we go to large scale, we can use process simulation that have been there for decades. And more recently, what are really exciting is these lab automation technologies and machine learning models that can help with doing the experiment and also handling the data. So, but our goal is not just to accelerate or speed up some individual step, but rather the whole process of materials development. So in order to do that, we need not just a higher throughput, but rather a faster turnaround by implementing this kind of closed loop framework where we have target design, then feed into automation and robotics that can do the experiment autonomously. And we can use either some fundamental foundation model or AI model to handle data analysis and decision-making in a higher speed, which hopefully can eventually feed into the loop again to suggest the next target or the next experiment. So back to 2020, when I was still at Berkeley Lab, we set up this goal to build an autonomous lab specifically for solid state synthesis and characterization of bulk powder inorganic materials, because those are the materials that are more relevant to the battery technology. So we envisioned such a lab that have robots that can handle powder precursors and products. We need some AI machine learning model that can do data analysis and decision-making. So eventually, we hope this lab can autonomously iterate towards a successful synthesis, so in this closed loop. We put a lot of effort in it, but before I go to the automation part, some of you may not be so familiar with this solid-state synthesis procedure. So it's one of the most traditional way to make oxide-based materials or some other ceramic materials. It's as simple as shake and bake. And in a laboratory, when we do it sort of in a manual process, we usually use this very commonly used instrument, and they are rather modular based and with a relatively small throughput. When it comes to the automation, it took us about 2.5 years to put up a design and implementation of some hardware together as well as the software. So this lab is currently located at Lawrence Berkeley National Lab in Berkeley, California. It's in a lab about 600 square feet. It has dispensing and powder dispensing and mixing station connected to some furnaces on the bench or on the floor. And then it has a powder retrieval station that I will show more details later, powder loading station that can do powder preparation for X-ray diffraction or for scanning electron microscope. So all these tools and the devices are connected and controlled by software and by computer written in Python. A particular challenge in this automation project is solid handling, and it's not just the powder handling, but rather solid handling after heating. Here I'm showing one example on the left side, how it looks like after high temperature treatment. So it's like a chunk of solid consolidated after high temperature, about 1,000 degrees C in a crucible. And what we need is actually fine powder that we can eventually go to do powder XRD or SEM. Again, in a manual process, it's not a big deal. It's kind of straightforward. You just need spatula and a mortar pestle to crush it to fine powder and maybe some glass slide to make the sample flat. But when we go to automation, especially in the context of materials discovery, we need to make sure that our lab is adaptive enough that it can handle all these variations in different chemical systems. And here, all of them are oxide-based, but still, sometimes you may have an empty crucible because something just evaporated. Sometimes we make this glassy form that is very hard to grind. You may have a chunky solid or a solid that is very hard to grind. Once in a while, we may have powder that is actually easier to handle. Even if we kind of, or the lab and the robots succeed in the powder step, after grinding, each powder may still have different flow properties. So how to dispense them correctly to the sample holder is also a challenge, and it's also something really important to ensure that we have good data quality afterwards. And of course, it's a robotic lab, so the robot needs to be smart enough to handle some small variations in the positions of vials, containers, or some holders. Some of the part of the lab we built in collaboration with some automation integration company, but the larger part of the lab we built up by ourselves through learning and doing, because we couldn't find a company that is willing to do something really new. So this station I'm showing here is a solid handling station after heating. We have some these crucibles that are taken out from furnace. And then this robot arm from Universal Robot, it can handle all this sort of powder sample or container transferring between different stations. We made most of things from 3D printing. For example, this milling ball dispenser was just, we just mimic the candy dispenser machine, $50 from Amazon, and some other things that we can easily make with a 3D printer. So for the robot arm, we put up some cameras and other sensors in it, so to make sure that it's smart enough to handle the variations. Example here, I'm showing that the camera can take pictures all the time to make sure that it has, like, the sample holder has enough coverage before it goes to the next step. Another example in this lab is that we implemented some dynamics, some mechanism to handle dynamic error to detect it and then self-calibrate it. Okay, so now I'm just going to show some of the integrated videos, which you can actually find on YouTube as well, of the whole process. So it starts with this automated powder dosing and dispensing. So now it shows how this auto balance is dispensing one of the precursors. It will then go to the next one, mix them up, and take it out from the mixer, transfer it to the crucible, and dry it out. Then the crucibles will be sent out to this front door, which goes to the next robot arm, pick it up from this front, carousel, and then send it to one of the furnaces. So it's either box furnaces if we do synthesis in the air, or tube furnaces if we need some controlled atmosphere. So after the heating step, it then goes to the station that I just showed, in which this robot arm can send the crucible to this vertical shaker to grind solid to fine powders. And then dispense it if we can obtain fine powders through this sieve cap. So once the sample is prepared, we can then the robot can then send it to this tabletop X-ray diffractometer, which is equipped with a machine learning model that can do multi-phase analysis of the obtained spectrum. So this model is specifically made for to deal with the trade-off between speed and resolution. So it will do a rough scan first, really quick scan, and then it will suspect should be scanned in more detail in order to have a more accurate face identification. So this model is based on a convolutional neural network, which was trained on all the known and hypothetical faces in a given chemical space. It's available on GitHub, so if you are interested, you can try it out. And this model also considered the perturbation to peak positions, peak broadening, or some intensity variation that comes from strain or some textures. But there, excuse me. All right. So is my sound okay?
Yeah, it's okay.
Okay, yeah, I think I probably need to wrap it up soon. So we are not so satisfied with using XRD only for the face identification, especially when there are multiple faces. So what we are doing right now is to combine the information from XRD with the chemical information from EDS elemental mapping, so to help with increased accuracy for the face identification. So far, what I've shown is the automation part, and every instrument and experiment data is controlled with this so-called ALab OS. It's an orchestra software package written in Python. So, and it's also accompanied with a dashboard or a GUI interface so that users without experience in Python can also use it smoothly. And we are also developing models to make sure that the lab is not just automated, but rather autonomous, which requires some AI agent to design the experiment. And there are two parts. The first part is to initialize experiment by sort of giving a suggestion on a reasonable recipe for the lab to try, which was based on a model trained on this text mining data from all the previous recipes people reported. But this doesn't always work out, right? Because we are dealing with, when we are dealing with new materials, the prediction might not always be accurate enough. So if that fails, we then use this active learning algorithm, we call it ARROS-3, that can learn from the failed synthesis outcome and then give suggestions on the new experiment. So I'm going to skip this part. And if you're interested in more details, you can check out our publications from last year. We tested with stable materials. We also tested with metastable materials, just giving an example here. And there are multiple steps that this model will go through. And many of the experiment can be skipped if it's predicted to be redundant. But in the end, I want to mention that we use this lab as kind of a recipe designing machine rather than the final stage. Once it gives us an optimal suggestion of recipe, very often we also do a standard synthesis by, for example, longer ball milling time will make a pellet or heating it longer to make sure that we can get a pure target. So to wrap it up, there are still a lot of challenges in hardware, software, and modeling, especially in the context here for solid-state synthesis. We have to admit that synthesis is a very data scarce area for AI and machine learning to really have an accurate prediction. So a very critical thing is that we need a better mechanistic understanding of what is happening behind the synthesis. And then our decision making is based on the data analysis, right? Which cannot be achieved just by using a one source of data. Many times we do need multi-source or multimodal data interpretation to make sure that we have a good prediction using the model. And hardware-wise, we also have a lot of problems with, for example, the containers, which are essentially the materials design problem as well. And we are also hoping to have more flexible and less expensive hardware. I think next speaker is going to cover a lot on this part. I'm very happy to be here and present our work. And I also want to thank my previous team at Berkeley Lab and also my current lab at FSU. Thanks, and feel free to reach out if you have further questions.
Thank you, Yan, for the nice presentation.
Thanks.